Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. Today's problem is how can you reversibly compress a string of bits? This is really good fun, but another reason we look at it at this particular point in the course, other than because it is such fun, is because there exists a very cool algorithm, due to David Huffman, for finding the optimal lossless encoding if you know the frequencies of the input symbols, and it is a greedy algorithm.
I am now going to talk about another greedy algorithm, which I find extremely exciting and inspiring and fun. And in the past, I would just introduce this, maybe make people write a program about it. This time, I've actually written a new section of the handout about it, which you will find. They're called Huffman codes. So Huffman codes are a way of compressing data. Imagine data just as a string of bits. In fact, in the context of Huffman codes, we just look at data as a string of symbols, symbols from some alphabet of a fixed size. They could be bits. They could more reasonably be something slightly bigger. They could be numbers. They could be characters. They could be bytes. If we think of bytes, then the bytes could represent anything. This is a digitized version of a picture that appeared in a newspaper. And this strip has been encoded in a bitmap file, Windows bitmap file, that stores each pixel of the image as 1 byte, that byte being an index into a lookup table of 256 possible colors. Now, all the colors that are used in this case are between black and white and some grays, but the bitmap could also look at other colors which are not used in this case. Anyway, so for each of the pixels in this image, the Windows bitmap file stores a byte, and plus some bytes at the beginning for some header information. So this happens to be 600 pixels across by 219 pixels down. So that gives us 131,400 pixels plus some junk for the header, another 88 bytes of header, and that's the total size on the disk. Now, if I look what bytes are in use in here, I can run this through a counting program, and I've written such a counting program. As you can guess, it's not difficult. It gives me a histogram like this of how many times each byte is used. So on the left here, I have bytes represented as either a hex number, or if they're printable, the printable version. Not that the printable version means anything in this case. I should have just put the hex value for everything, but I had written the counting for another purpose, so I just recycled it. And this bar says that the 00 byte is used basically 100,000 times. These other ones, 1, 2, 3, 4, are used a few thousand times each. This 7 is used 11,000 times. And then these other ones, there's a tail of things that are used just a single digit number of times, 3 times, 2 times, 2 times. So it's an easy guess that this is the white, this is the black. These are some of the grays that are in here, and these are some grays that rarely occur. You could imagine just getting rid of these, and the picture wouldn't noticeably change. If you had just this and this, it would still be recognizable. We would just look a bit more crude in the details. An obvious way to compress this would be just to get rid of these, and I'm left with only 8 different values to encode, which don't really need 1 byte each. 8 of these will only need 3 bits each, and so I already get a reduction by a factor 3/8 in this number of bits that I need to store in order to encode that. And that's nothing special, but I'm just saying I don't want to pretend that I am getting a big gain when an obvious big gain could be had with much simpler techniques. So, but still, compared to the value this number times this number, is there a more efficient way of encoding this picture? Based on the same idea of Morse code, that if there is something that I know about the frequency of occurrence of the various symbols in my input stream, if some symbols occur much more frequently than others, this one occurs 100,000 times and these other ones a few thousand, this one 10,000, then it might be a good idea to make the symbol that occurs 100,000 times shorter than these other ones. And then even if some of these become longer, because on average they would all be 3 bits. If I make this one shorter than 3 bits, something will have to be 4 bits. But if it occurs so much less frequently, I may still have a gain overall. So the idea of the family of codes that we are looking at is to take symbols that are encoded with a fixed number of bits each and make a bijection between those symbols and other code words which may have variable length in bits, and allocating shorter codes to the more frequent source symbols, so that these shorter code words will give some saving when they are strung together. And this is something that you can only do if you know something about the frequencies in the input. If you don't know anything, then there's no reason to make any symbol any shorter than any other. And in fact, it is possible by this technique to make the output longer than the input, which is not advantageous for the purpose of compression. But if you know about the input statistics and you use them properly, then it is possible to make a gain. If I'm going to encode things into code words of variable length, I have a problem of how to decode if nobody gives me the boundaries between these code words. If some code words are 1 bit long, some others are 2 bit long, some others 3 bit long, some others 5 bit long, if I get 1, 1, 1, 1, 1, 1, 1, how do I know if it's a 1 followed by 2 1s, followed by a 1, followed by 3 1s, or if it was just individual 1s, or if it was just one long code of 5 1s plus another one of 5 1s? How do I know? So Morse code cheats because Morse code adds extra space between the dots and dashes. We are not allowed to do that. We only have 0s and 1s. So if we are not allowed to cheat in the way Morse code does, what we need to do, well, one solution to that issue is to make a code where it is uniquely determined which code word can come out of a string, no matter how long it is, because no two code words start in the same way. So no code word is a prefix of any other valid code word. Are you with me? So not all possible choices of code words enjoy this property, but it is possible to decide, this is going to be one of my rules, I'm going to only make codes where the family of code words never has one code word as a prefix of any other code word. This family of codes is called prefix codes. If we were logical about it, we would call them prefix-free codes, but the custom is to call them prefix codes. How do you build a prefix code? If you think about it, a prefix code is what you get when you have a tree like this one, where every node is either the parent of 2 children or the parent of no children. So this node is a parent of 2 children, it's a parent of 2 children, this one is the parent of no children. There's no node that is a parent of just one child. In this type of tree, you can call the nodes that have no children the leaves of the tree, and the leaf of each tree is associated with a code that's obtained by taking the bits on the branches that lead to it from the root. You call left 0 and right 1, and then from the root you take, that's the 0 child and the 1 child. 0 child at 1 child, 0 child at 1 child. So the code for this is 0, 0, the code for this is 0, 1, 0, the code for this is 0, 1, 1, and so on. And it's fairly obvious from this example that if you build your code in this way, it is impossible for any code word to be a prefix of another code word, because for a code word to be a prefix of another code word, you would have to have a code word somewhere and then continue with something else after it. But you can't do that if you said that you can only have nodes that either have no children, in which case they are leaves, and that's where the code words live, or they have 2 children. Because if you are a code word, then you're not going to have children, and you're not going to be able to continue into something else, of which you would be the prefix. So this is a procedure for building a prefix code. Just build yourself a tree like that. So if we think of our frequencies here, when I was writing the handout, I was attempting to be pedantic about the distinction between number of occurrences and frequencies, which some people might describe the frequency as more like the probability. So like the frequency of this one is 1/10 of the total. So all the frequencies would add up to 1. But not everybody is consistent about this. So some people just say, and I think also your book just says, if this occurs 2,788 times, then its frequency is 2,788 in the context of that file. So in that case, you just take the total of all these and divide this thing by that number in order to obtain the probabilities, or the things that would then add up to 1 altogether. So for the purpose of not having numbers with too many digits, which would slow down the calculations, I've taken the numbers in here, and I've just taken how many, I've truncated it to the hundreds. So if this is 2,788, I called it 27. 3,614, I called it 36. And I copied them down in here. So the symbol 00 is worth 1,010. The symbol 01 is worth 27. The symbol 02 is worth 36, and so on. So I can, this is a representation of this histogram. So I can make any code I like within prefix-free codes just by building a tree out of these leaves. So I build the tree bottom up. And what I would do is something like this. I take 2 of these, and I make a node. I take 2 of these, and I make a node. I take 2 of these, and I make a node. I don't have to. I could take this and this, and I make a node. I could take this and this, and make a node. This and this, why not? This and this. That's a tree. And so that would give the following codes. So this one, this is 0, 0, would be symbol 0, 0. This is 0, 1, 0, 1. This is 0 and 0 and 1. So this would be, but there's a 1 here, so this would be 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0. So it's 1, 1, 0, 0, 0. And so on. And I assign a unique code to each symbol in a way that ensures no code word is a prefix of any other code word. And if I did that, I would have a code, and I could encode the original file in this way. And I might ask myself, how many bytes will 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. I might ask myself, how many bits would I use if I used this code instead of the original code? You have a question? Yes? Oh, excuse me. I'm very sorry. Yes. If I do this thing, which is because they still haven't fixed the projector, it's not projecting as much as my screen, then please feel free to actually make sounds and say, hey, I am not seeing what you're doing. We are wasting time. You'll have to restart again. So don't be so polite that only if I look in your direction I will notice. If it then takes 10 minutes for me to look in your directions, we are stuck. So my apologies for this. I was drawing at the bottom of the screen the code words that you obtain by following through the branches. And I hope I haven't made mistakes in copying them down, but I hope one of you will alert me if I have. So my next job is to say, how much would this cost? So the cost of a code, I can, in terms of the compression, I can just talk of the cost of a code in general, regardless of the input. If I know the frequencies of the input symbols, then if I have another input with the same frequencies, that's fine. If I have a much longer file, so long as it has the same frequencies, the efficiency of the code on it will be the same. So I can talk about the cost of a code as basically the average length of the encoded symbol through that code weighed by the frequency of the symbols. Am I making sense? So if I have the source where every source symbol is encoded with the same number of bits, in my example 8 originally, or 3 if I get rid of the total wastage, then clearly the average of space used by each symbol is 3 bits because it's the same for all of them. But if I have a variable length code like this one, some bits are encoded, some symbols are encoded with 2 bits, some symbols with 3 bits, some symbols with 5 bits, some symbols with 4 bits. On average, what's the average length? Well, it's not the sum of these things divided by 8. It's the sum of this weighed by their frequencies, then, which should all be divided by the sum of the frequencies, so it adapts to 1. And then that will give me the weighed average of the length of these, and if this weighed average is less than 3 bits, then I'm using less than 3 bits per code word, and I am making a compression. And if it's greater than 3 bits, then I'm not making a compression, and it's not a good code to use if I wanted to compress. Am I making sense? Good. So the sum of these frequencies over here okay, 10, 10 plus. I'm adding up all these things here. 10, 10 plus 27 plus 36 plus 41 plus 31 plus 21 plus 26 plus 117 is 1,309. So the probability of each of the input symbols would be the number that I have here divided by 1,309. And if I multiplied that fraction by the length of this and added them all up, so 1010 divided by 1,309 times 2 bits, this one divided by this times 2 bits, this one divided by this times 3 bits, and I added all these up, that would be the cost of my code. Every time I decide to pair up 2 of these, I am making a choice. And you can see, if you're smart, you will have noticed the isomorphism between this and a problem we did a lecture or 2 ago, where I was trying to multiply matrices, where ultimately the choices I was making was which 2 matrices do I multiply at a time. And so this gave rise to a number of possible trees that I could rearrange this into. And there were a Catalan number of trees, which grows more than polynomially. And so I said, I don't want to look at all these trees. And here is the same. There's an exponential number of these trees that I could build. And I don't want to have to look at all of them. But each time that I pair up two things, I'm making a choice. And I would like to make the greedy choice. I'm talking of Huffman codes as an example of greedy. Where's the greed in that? How am I making a greedy choice? Well, the greedy choice would be the one that leads to the least expensive code. And so if I could somehow define what is the contribution of each of these decisions to the final cost of the code, then I could take the decision that costs the least. So pay attention to this, otherwise you will get really lost in what I do next. And when I was rereading my handout to prepare today's lecture, that's the point where I said I must explain this really clearly, because otherwise I get lost as well. So the total cost of this code is given, as I said now several times, by the length of each code word weighed by the frequency. So the length of each code word is the length of the path from root to leaves. So I can say the cost here is this length 2 times this. This length 2 times this. And I'm ignoring the division by 13 or 9. I can do that at the end. So when I'm still in the process of building up this code, I'm halfway through. So let me just get one of these to start afresh. I made myself some copies before I came here of this bottom part. And I say, okay, the first thing I do is I pair up these two. What's the cost of this operation? Well, it doesn't really have a cost because I haven't made a code. It's not a code because it can't encode anything. It can't encode the arbitrary inputs with those symbols. But what could I define as the cost contribution of this towards the total cost? Well, one definition that I came up with, which I think is sensible and consistent with the rest of the stuff I said, is let's take the length of each code word. So at the moment, I've only made code words for this one, which would be 0, and this one, which would be 1, and these ones don't have a code word. Because they don't have a code word, the code is incomplete and doesn't work. But because they don't have a code word, the length of the code word is 0, and so they don't cost anything. So although this code is incomplete, its cost would be 1 for this and 1 for that. So the cost would be 1 times 1010 plus 1 times 27. So it means just add this up. So that's 1037. And I write this cost in here. If I were to take another decision, which might be I'm going to take this one and this one, what would be the cost of the code resulting from all that? Well, the new code would now have this, and it would also have a 0 for this and a 1 for this. We can see it's not a proper code because there are 2 symbols that reuse the same code word and 2 other symbols that reuse the same code word. So things are still incomplete. It's not properly a code. But on the way to making another code, I have made another word of length 1, which is going to be used 21 times. Another one of length 1 that's going to be used 117 times. So the cost contribution of this new decision I've taken is going to be 21 plus 117, which leads me to 139. So if I were now to add another node that doesn't take 2 leaves, but takes an existing node and a leaf, or an existing node and another existing node, for example, this, what would I be making? Well, I would be making a new code that's 0, 0 for this. So this changes to 0, 0. This changes to 0, 1. Sorry, yeah, 0, 1. This one changes to 1. And so the cost of this symbol in the code form so far would be 2 times 1010. The cost of this symbol would be 2 times 27. The cost of this one would be 1 times 41. This one 1 times their own frequencies. But, important, what is the cost of this particular decision of merging this and this? The cost of this particular decision is the sum of all the things I just said minus the sum of all the things that existed before I took this decision. So the cost of this particular decision is just the increment in cost from the previous incomplete code to the current incomplete code. And this extra cost is just adding one more leg to these two and one more leg to this one. That's a crucial point. Does this make sense? You can develop the algebra and see that this one now becomes 2, but you can subtract the 1 that you had before. So all that really matters is that each one of these extra things I do, each one of these, like that, just contributes its 2 branches. So one for this and one for this, one for this for all of these, and one for this for these, right? So the contribution of this is actually this times the sum of all these, this. Not this one because it's not part of this tree. And this one is the sum of this and this. But cleverly, the sum of this and this is already written in this node. And the sum of this is already written in this node because that's how I'm building them up. So really, in each node, what should go is the sum of the 2 nodes that it merges, right? So if you are paying attention all along, it makes sense. But you are in an elite because other people got lost at some point and are not following anymore. But they will have to work it out. I've made a point of having an exercise in your handout at this stage where if you haven't been following, you can redo it yourself. And then hopefully the coin will click. So at this point, I can say the cost of each decision is the number that I have in here, which is the sum of the frequencies of the things I'm merging. And so the greedy choice would be always to take the merge that has the lowest cost. That's the greedy choice that Huffman takes, and that's how I build a Huffman code. I build a Huffman code by always merging the 2 lowest frequency emerging things. And if I do that, I am getting a code that is minimum possible cost among all the prefix codes, and it is possible to prove that non-prefix free codes cannot do any better, and therefore it's worthless even looking at them because they only cause trouble, and so it is the best of all these codes, and it's given by Huffman. So what would we do in here? We would if I start with a blank one, if we wanted to build ourselves a Huffman code, we would take the 2 lowest frequency symbols, which happen to be 21 and 26. We would make them into a node like this, and we would label this with the sum of their frequencies, 47. And then we would take not the smallest 2 leaves, but we would take the smallest 2 emerging things. So it could be that the smallest one is this one and this one, which happen to be 2 leaves, but it could have been a leaf and another tree, and so on. And the way that I actually write the code is to say, when I build myself this node, which replaces those 2 with the sum of their frequencies, I also want this to be considered in the sequence of things out of which I will make the next decision. So my easiest thing is just to dump all these frequencies into a min heap, and then take the minimum of the min heap twice, add them together, and stick it back into the min heap. And wherever it comes from, the next 2 things are going to be the best 2 things to merge. And I keep going until the min heap runs out of nodes to merge. And when there's only one node in the min heap, it means I've reached the root of this tree, and then I've built the whole code. So this is how you do the Huffman code. And if you were to do that on the example we had, you would reduce things from 3 bits per code word to something like 1.58 bits per code word. I'm not going to try and do it on the blackboard because it takes a long time, but I think I've given you enough to make you want to go and try it yourself. All right, I am very happy today because I have evidence that some of you have been doing the exercises I suggested in the handout, where there's a blank for you to fill in and do some of these computations. Also, a couple of you came to see me at the end of last lecture to ask something that is interesting to share with everyone. I meant to say, but there were so many things to say that I didn't say, and I still wanted to say, so I'm going to say it now. So when you are building up a code, not necessarily the Huffman code, which is the best, the optimal code, you're building a code, any prefix code, out of some symbols for which you know the frequencies. You build the code by combining subtrees and recording the aggregate frequency of the things you merge. So if this one had 31 and 21, you merge them together, then you add them up, and it's 52. If this whole thing had an aggregate frequency, these 4 symbols together, you add these up, it's 195. And you combine them with this other thing, which has an aggregate of 77, then the aggregate of everything is 272. Okay, so that's pretty obvious. The thing that is subtle is that the contribution of each decision to the total cost of your code is exactly the value that's in the node of the 2 things you merge. So every time I decide to merge something, I'm taking a decision because I could have merged 2 other things. And the cost of that particular decision is the number in the node, so the sum of the 2 things that I am merging. And the cool thing is that each one of these is a contribution to the total cost. If you add all of these together, you get the total cost of the code. So you can then go back and say, oh yes, the code costs a lot because principally of this decision I made. And if you started by merging this and this, for example, 1010 and 27 makes 1037. This is because at the time you only have these. At the time the only decision you've taken is this. Then you have a forest whose cost is having one symbol of length 1, that would be just 0 for this symbol, one symbol of length 1, this 1, and this symbol occurs 1010 times, this symbol occurs 27 times, each of them has length 1, so that's the total cost. When you had another one in, for example, this one, then again you've created 2 more strings of length 1. This one over here occurs 31 times, this one here occurs 21 times, so you add 31 and 21 to the cost. And this is not yet a code because there are things that are 2 different symbols that use the code word 0 and a number of symbols that don't have any code words. So it's not a proper code, but this is its cost so far. Now, the total cost of my code is the sum of these numbers in here, each one of these blobs together, and each one of them incrementally. At the time that I was building up my code, that's one decision that cost me 1037. That's a decision that cost me only 52. That decision cost me 78, and so on. And if I add them all up, I get the cost of this code. Adding up all these numbers gives me 3020, and the real cost in bits is obtained by dividing this by the total frequency, which is the sum of all these. So the sum of all these which is this, divided the sum of all these, which is this, gives me the cost of the code as bits per code word on weighted average. That's 2.3 bits for this code. And of these 2.3 bits, then this decision here contributed 52 divided by 1309. .0038 bits. So that was a very cheap decision to take. This one was a much more expensive decision to take, is almost one bit it cost me to do that. And so you can see that Huffman is greedy because at every stage it takes the decision that costs the least, and then the sum of all these things is going to be the smallest. All right, and I'm pleased that some of you were doing this exercise, even finding mistakes in them. So I found a mistake before last lecture, and I put it on the web page. This morning, two people reported 2 more mistakes, and I will put them on the web page as well, so you can correct your handout.